Hi everyone, welcome back to Coding Fab. Today we're diving into the world of machine learning, one of the most exciting and fast-growing areas in tech. In this lesson, we'll start by answering the big question, what is machine learning? Then we'll explore how it works, look at real-world examples, and break down the different types of machine learning like supervised, unsupervised, and reinforcement learning. We'll also touch on the differences between AI, machine learning, and deep learning to help you see the bigger picture. For each category, we'll walk through real-world tasks so you can see exactly how these techniques are applied, from predicting house prices to classifying handwritten digits, detecting vehicles, grouping customers, and even training an agent in a game. If you're new to this topic, don't worry, we'll take it step by step. All right, let's get started. 1. Introduction. What is machine learning? Machine learning is a subset of AI that enables systems to learn from data and to make predictions or decisions without explicit programming. Let's compare it to humans. How do humans learn? We learn by observing, practicing, and getting feedback. Machine learning is about teaching computers to do the same. Learn from data and make decisions without being directly programmed. In traditional programming, a human writes the rules. You give the computer those rules along with some data, and it follows the instructions to produce the result, such as a calculator. You write the formula and it answers. In machine learning, it's the opposite. You give the computer data and the correct results, called labels. And the computer figures out the rules by itself. For example, let's think of an email spam filter. You show it many emails labeled spam or not spam, and it learns how to spot spam on its own. So instead of writing a long list of if this, then that rules, machine learning learns the rules by finding patterns in the data. 2. Basic machine learning process. Here is the basic machine learning process. 1. Data collection. First, gather relevant data from various sources like CSV files, databases, sensors, APIs, web scraping, and more. The data can come in different forms such as tabular data, images, text, audio, or video depending on your task. 2. Loading the data. Load the collected data into your programming environment using tools like Pandas for tabular data, OpenCV or Python imaging library for images, or libraries like NLTK for text. 3. Exploring the data. Understand the data set by checking its shape, types, summary statistics, and visualizing distributions. This helps reveal patterns, imbalances, or errors. 4. Cleaning the data. Fix issues in the data by handling missing values, removing duplicates, correcting data types, and ensuring consistency across columns. 5. Feature selection. Choose the most important features that will help the model make accurate predictions. Irrelevant or redundant features are removed at this stage. 6. Pre-processing the data. Convert data into a format suitable for machine learning. This includes scaling numeric features, encoding categorical variables, tokenizing text, normalizing images, and splitting into training and test sets. 7. Training the model. Feed the processed training data into a machine learning algorithm such as linear regression, logistic regression, and neural networks. The model learns patterns and relationships between input features and the target. 8. Make predictions. Once satisfied with the model's performance, use it to make predictions on new unseen data or integrate it into an application for real-world use. 9. Evaluate the model. Test the model's performance on unseen data using metrics like accuracy, precision, recall, F1 score, or mean squared error. This helps determine if the model generalizes well. Of course, the order may vary depending on the task and analysis method, but basically, we will follow this procedure. 3. AI, machine learning, and deep learning. AI is the broadest concept. It refers to machines or systems that can perform tasks that usually require human intelligence, like thinking, learning, or problem solving. For example, a robot that can walk, recognize your voice, and answer questions. As we learned earlier, machine learning is a subset of AI. It focuses on teaching machines to learn from data and improve their performance without being directly programmed. For example, Netflix recommending movies based on what you've watched. Deep learning is a subset of machine learning. It uses advanced models called neural networks that are inspired by how the human brain works. Deep learning is especially powerful for large and complex data like images, videos, and natural language. For example, self-driving cars recognizing stop signs and pedestrians using cameras. Overall, AI, machine learning, and deep learning are closely related concepts, but they differ in scope and complexity. In essence, AI is the umbrella, machine learning is a subset of AI, and deep learning is a subset of machine learning. 4. Machine learning versus deep learning. Let's take a closer look at machine learning and deep learning. Machine learning refers to techniques that allow computers to learn from data using specific algorithms. These algorithms include things like linear regression, decision trees, support vector machines, and k-nearest neighbors. In machine learning, human intervention is often required to manually select and engineer features, the input variables that help the model make accurate predictions. For example, in a sales prediction model, a data scientist might decide to include features like past purchase history or location. In contrast, deep learning is a more advanced form of machine learning. It uses complex structures called neural networks that have many layers, hence the term deep. Popular architectures include convolutional neural networks for images and recurrent neural networks or transformers for text and sequences. A key advantage of deep learning is that it can automatically learn features from raw data, such as pixels in images or words in sentences, without requiring manual feature engineering. Another one of the biggest differences between the two lies in data requirements. Machine learning works well with small to medium-sized data sets, making it suitable for many practical business applications. Deep learning, on the other hand, often requires very large data sets to perform well and to avoid overfitting. This is why deep learning is typically used in tasks involving massive amounts of unstructured data, like thousands of images or millions of text documents. Another key distinction is in training time and computational power. Machine learning models are usually faster to train and can run efficiently on standard computers. Deep learning models are slower and require more processing power, often using specialized hardware like GPUs to handle the large amounts of computation needed during training. In terms of interpretability, machine learning models are generally easier to explain. You can usually understand why a decision was made, especially with tree-based models or linear regression. Deep learning models are often considered black boxes. They may perform exceptionally well, but it's harder to understand how they arrived at a specific output. When it comes to types of data, machine learning typically works with structured tabular data like spreadsheets, survey results, or database records. Deep learning is better suited for unstructured data, such as images, video, audio, or natural language text. Lastly, their use cases differ. Machine learning is widely used in tasks like credit scoring, spam detection, and sales forecasting. Deep learning is preferred for more complex applications like image classification, speech recognition, language translation, and even autonomous driving. 5. Types of machine learning. Machine learning is mainly divided into 3 types depending on how the model learns from data. First, supervised learning. In supervised learning, the data comes with labels, which means the correct answers. The model learns from these labeled examples and tries to predict the correct output for new and unseen data. For example, if you give a model many images labeled cat or dog, it learns to recognize and classify them correctly. Common use cases are email spam detection, predicting house prices, and recognizing handwritten digits. Second, unsupervised learning. Here, the data has no labels. The model looks for patterns, groups, or structures in the data all by itself. For example, grouping customers based on shopping behavior without knowing who they are, such as big spenders, high spend, low frequency, regular shoppers, frequent purchases and average spend, bargain hunters shop mostly during sales, browses, visit often but rarely buy. Common use cases are customer segmentation, market basket analysis, and data compression and noise reduction. Third, reinforcement learning. This type is like training a pet or playing a game. An agent, or the learner, interacts with an environment, takes actions, and receives rewards or penalties. Over time, it learns to make better decisions to maximize rewards. Common use cases are robotics, self-driving cars, and game AI. 6. Overview of machine learning tasks. This table represents machine learning tasks, including task types, data types, popular algorithms, and examples. Let's quickly walk through the details. Supervised learning uses labeled data where both the input and the correct output are provided. The goal is to teach the model to predict or classify new data. For regression tasks using tabular data, models like linear regression are used to predict continuous values, such as estimating house prices or forecasting sales. In classification tasks with tabular data, models such as logistic regression, decision tree, random forest, XGBoost, KNN, SVM, and neural networks are used to categorize data into classes. A typical example is detecting whether an email is spam or not. When dealing with image data, convolutional neural networks, CNN, are used for classification tasks like recognizing handwritten digits. For text data in natural language processing, models like RNN, LSTM, and transformers like BERT and GPT are used for tasks such as sentiment analysis or email classification. In computer vision, the goal is not just to classify objects but to locate them within an image or video. Algorithms like RCNN, YOLO, SSD, and efficient det are used to detect faces or identify objects for self-driving cars. Next, unsupervised learning. Unsupervised learning uses unlabeled data and focuses on finding hidden patterns or groupings. A common task here is clustering, where algorithms like k-means are used to group data points that are similar to each other. This is useful for tasks such as customer segmentation or discovering topics in text without predefined categories. Lastly, reinforcement learning. Reinforcement learning involves a learning agent that interacts with an environment and learns by receiving rewards or penalties for its actions. Algorithms like Q-learning, deep Q network, DQN, and policy gradient methods help the agent learn which actions to take to achieve the best outcomes. Examples include game-playing AIs like AlphaGo or training robots to perform tasks like walking or navigating a space. 2. Python for machine learning. Python has a huge number of libraries for data and machine learning, supported by a strong community and tons of tutorials. These are key Python libraries used in machine learning, along with what they're used for and examples of how they help. NumPy is used for numerical operations. It helps you create and work with arrays, vectors, and matrices, which are the building blocks of machine learning data. Pandas is great for handling and cleaning data. You can easily load CSV files, filter rows, sort values, and prepare your dataset for analysis. Matplotlib and Seaborn are used for visualizing data. They let you create charts and graphs to better understand the patterns in your data. Scikit-learn is a core library for machine learning. It includes tools for building models like regression, classification, and clustering, all in a beginner-friendly way. TensorFlow and PyTorch are powerful deep learning frameworks. They're used to create more advanced models like neural networks, including those for image and speech recognition. Please check the other videos to learn how to use each tool. 3. Supervised learning. 1. Regression. Regression is a type of supervised learning used when the goal is to predict continuous numeric values. This means the model learns from labeled data where the output is a number, such as price, temperature, or score. Some common task types in regression include simple linear regression, where there is one independent variable, and multiple linear regression, which uses two or more independent variables to predict a continuous outcome. Regression typically works with tabular or numeric data, like spreadsheets containing numerical features such as age, income, or sales figures. Popular algorithms used in regression tasks include linear regression, random forest regression, decision tree regression, support vector regression, and XGBoost, which are all designed to estimate numerical outcomes based on input features. To evaluate how well a regression model performs, we use metrics like mean squared error, root mean squared error, and R-squared score. These metrics measure how close the predicted values are to the actual values. Common real-world examples of regression include predicting house prices based on features like size, location, and number of rooms, forecasting sales for the next quarter based on historical data, and estimating temperatures using environmental and seasonal variables. From the next section, let's practice on the real-world tasks. Medical cost prediction. This project is a regression-based machine learning task focused on predicting individual medical charges using personal and lifestyle attributes such as age, BMI, number of children, gender, smoking status, and region. The dataset, sourced from Kaggle, is in tabular format and well-suited for applying supervised learning techniques. The goal is to develop a model that can estimate medical costs based on these features, providing insights into which factors contribute most to variations in healthcare expenses. Linear regression is chosen for its simplicity and interpretability, and categorical variables were handled using one-hot encoding during pre-processing. The project was implemented in Jupyter Notebook, utilizing essential Python libraries, such as pandas for data manipulation, scikit-learn for modeling and evaluation, and matplotlib and seaborn for data visualization. All right, let's dive in. 2. Data collection. Let's download the dataset into your system. In this example, we use the Kaggle Medical Cost Personal Dataset. Kaggle is a popular machine learning platform with datasets. You can find the dataset from the dataset page on their platform and download it as a CSV file. It looks like this. You'll see the features such as age, sex, BMI, children, smoker, and region, and the target label, which is charges. Three, load the data. After downloading the data, open your preferred IDE such as Jupyter Notebook and create a new notebook. Also upload your dataset. You can paste it to the same folder. Then import pandas and load the CSV file by using pandas read CSV to load the dataset into a data frame. Data frame is often named as DF for short. Also make sure the file name matches exactly what you uploaded. In this case, insurance CSV. Now you can view the first few rows using head method to see what your data looks like, such as the target label charges and other features. 4. Explore the data. Before you build a model, you need to understand your data and make sure it's clean. Dirty or messy data leads to bad predictions. For example, info method shows a summary of the data frame structure, including the index range, number of columns, column names, non-null values per column, and data types. It says the total entries are 1338 rows and no missing values. Numerical columns are age, BMI, children, and charges. Categorical columns are sex, smoker, and region. Another method is describe. It shows a quick summary of your dataset. For numeric columns, count, mean, standard deviation, min, 25, 50, 75%, and max. For categorical columns, count, unique, top, and frequency. Let's quickly highlight the key insights. First, age ranges from 18 to 64. Median is 39. 676 are males. BMI ranges from about 16 to 53. Median is about 30.4. As for children, most people have 2 children. Max is 5. 1064 out of 1338 are non-smokers, very imbalanced. Most people are from the Southeast, 364 people. Charges have a huge range from 1,121 to 63,770. Very skewed. So we can get a lot of information in this step. These are the other useful exploration methods. Please try them out and explore the data further. The details of each method are explained in the other video. And also, visualization is important in the exploring step. It helps detect patterns, spot outliers, understand correlations, and present insights more easily to others. These graphs are drawn using the format shown in the lower right. It imports Matplotlib and Seaborn first. Then create a canvas and set the size of the plot. After that, write a main plotting command which can be replaced with a hist plot for distributions, scatter plot for relationships between 2 numerical variables, and a box plot for comparing distributions across categories. You can pass the relevant data frame columns to those functions. Then set your chart's title and axis labels to clearly explain what the viewer is seeing. Finally, display the plot with the show method. Alright, let's walk through each graph step by step. First, the distribution of medical charge is shown in the upper left. The distribution is skewed, long tail on the right. Most patients are charged under $15,000, but a few have very high charges. Seems to have outliers. So we can consider transforming the target variable if needed for certain models. Next, medical charges by smoker status. This graph shows that smokers have significantly higher medical charges than non-smokers. The median charge for smokers is over $30,000, while it's below $10,000 for non-smokers. So this is a strong indicator that smoker is a powerful predictor. Next, sex versus charges. The box plot shows that there is no strong relationship between sex and their medical charges. Both males and females have similar distributions with overlapping medians and comparable variability. Therefore, while sex can still be included as a feature for completeness, it does not appear to be a strong predictor of medical costs on its own. Next, charges versus BMI colored by smoker. Smokers with higher BMI tend to have very high charges. For non-smokers, charges remain lower even at higher BMI levels. BMI alone has a moderate effect, but in combination with smoker, the effect is strong. Next, charges versus age, colored by smoker. Charges increase with age, especially for smokers. Smokers are consistently charged more across all age groups, so there is a strong relationship between age plus smoker and charges. Next, medical charges by region. There is no major difference across regions. Slightly higher charges in the Southeast region. So region may not be a strong predictor, but still useful for completeness. 5. Cleaning the data. Before moving forward with modeling, we'll do a data cleaning step to ensure the data set is accurate, consistent, and free of issues that could negatively affect model performance. First, we check for missing values using the Isnell sum method. Fortunately, there are no missing values in any of the columns, so no further action is needed in that regard. Next, we check for duplicate rows using duplicated sum. We see one duplicate record which can remove using drop duplicates. Removing duplicates helps prevent bias or overfitting during training. Next, inconsistent data. Check the categorical data like sex, smoker, and region by examining their unique values, because sometimes there are typos. But seems like all values are consistent and clean, no typos, unexpected values, or formatting issues. So we didn't need to make any corrections here. Finally, look for outliers, particularly in the charges column, using a box plot. While observing some high medical charges above $50,000, these are likely legitimate cases, like smokers with health issues. So for now, let's keep all data as is and ignore outliers. Here's the quick summary of this step. If you have missing values, you can follow these strategies. Here's a quick summary of options to handle missing values for numerical columns and categorical columns. For numerical columns, there are largely 7 ways. Mean imputation replaces missing values with the average of the column. It's simple but sensitive to outliers. Median imputation is better for skewed data because it's less affected by extreme values. Mode imputation fills missing numbers with the most frequent value, useful for discrete numerical values. Constant value lets you fill in a specific number like 0 or 1 to indicate missingness clearly. Interpolation estimates missing values by looking at neighboring data points. This is ideal for time series. Predictive modeling uses machine learning or regression to estimate missing values. This is accurate but complex. Drop rows removes records with missing values, best used when only a few rows are affected. For categorical columns, there are largely 5 options. Mode imputation is most common. It fills in the most frequently occurring category. Constant label lets you insert placeholders like unknown or missing to indicate data was not provided. Frequency encoding uses your domain knowledge to insert the most common or likely category. Predictive modeling predicts the category based on other features. More advanced but effective. Drop rows removes missing entries if they are rare or not critical to your analysis. Here are the tips for choosing a strategy. Use mean or median for numerical values depending on the distribution. Median is for skewed data. Use mode or unknown for categorical data. Drop rows only if the number of missing values is small. For critical columns with many missing values, consider domain knowledge or predictive modeling. 6. Feature selection. In this step, you'll separate the dataset into 2 parts. Features, the input values the model will use to learn patterns. And target, the value you want the model to predict. This step matters because your model learns from features to predict the target. So choosing the right features is critical for accuracy. To select the most relevant features for predicting medical charges, we used a combination of domain knowledge, correlation analysis, and visualization. From a domain knowledge perspective, it's reasonable to assume that a person's age, BMI, number of children, and especially whether they smoke, would significantly impact their medical costs. Additionally, factors like gender and region may contribute to variation, even if the impact is smaller. To support this, we check the correlation. Since correlation analysis only works with numeric data, first convert the categorical variables such as smoker, sex, and region into numeric form using the map method and encoding. This allowed us to compare them directly with the target variable charges in the correlation. Note that while smoker and sex are binary and can be directly mapped to 0 and 1, the region variable has more than 2 categories and no inherent order. Therefore, it requires one-hot encoding, which we will implement properly in the pre-processing section. Next, visualization. We visualize the data using scatter plots and box plots in the exploring data section like this. Those reveal that smokers consistently have much higher charges, and that older individuals and those with higher BMI also tend to incur greater costs. While the impact of region and sex is less clear, we will include them to allow the model to capture any subtle trends. Based on these insights, decided to select the following features for our model: age, sex, BMI, children, smoker, and region for features, and charges for the target value. 7. Pre-processing. The main goal of the pre-processing step is to prepare the raw data into a format that a machine learning model can understand and learn from effectively. This includes handling categorical variables, splitting the dataset for training and testing, and optionally scaling numerical features. Proper pre-processing ensures that the model trains accurately and generalizes well to new data. First, we apply one-hot encoding to convert categorical variables into a numeric format. This is necessary because machine learning models like linear regression can only work with numerical input. We use the pandas getDummies function with drop first true to avoid the dummy variable trap, which can cause multicollinearity. This approach replaces each categorical column with a set of binary 0 or 1 columns representing each category, excluding 1 as the reference. For example, the smoker column is transformed into a single binary column, smoker underscore yes, while region, which has 4 categories, is converted into 3 binary columns, like region northwest, region southeast, region southwest, with one region dropped as the baseline. More specifically, if we don't use drop first, region has 4 unique columns. Each of these columns indicates whether a row belongs to that specific region, 1 or 0. However, this introduces a problem known as multicollinearity, when one feature can be perfectly predicted from the others. This redundancy can confuse the linear regression model, leading to unstable or inflated coefficient estimates. That's why we have to drop one category like this. Now the dropped category becomes the baseline or reference group. The model will compare the effect of other regions relative to this baseline. After pre-processing the features, we split the data into 2 parts, a training set and a testing set. The training set is used to teach the model, while the testing set is used to evaluate how well the model performs on new, unseen data. We typically use an 80 and 20 split, where 80% of the data is used for training and 20% is used for testing. This approach helps prevent overfitting and provides a realistic way to measure model accuracy. We use train-test-split from scikit. Learn to do this efficiently, ensuring the model is trained on a representative sample and evaluated fairly. We don't not apply feature scaling here, as it is not required for basic linear regression, when all features are already on a similar scale or are one-hot encoded. Next, train the model. The goal to use the training data to teach the model how to make predictions. During training, the model looks at the input features and tries to learn how they relate to the target values. Linear regression finds the best fit line by minimizing the difference between predicted and actual values. This is called minimizing the error or loss. Let's use linear regression from scikit-learn. First, import the model and create the model. Then train the model using the fit method. Now the model has learned the relationship between the features and the target. After training, you can check feature coefficients and intercept. They are used to check the learned equation. Coefficients give you a list of weights or slopes for each feature. These values tell you how much the predicted medical charges change when that feature increases by 1 unit, assuming all other features stay the same. Intercept is the value of charges when all feature values are 0. It represents the baseline medical cost before adding any influence from the input features. For example, this is the result of coefficients. It shows high positive coefficient, so being a smoker significantly increases predicted medical charges compared to a non-smoker. On the other hand, region Southeast has a negative coefficient, so people in the Southeast region are expected to have lower charges than those in the base region. The intercept might be large, but doesn't always have practical meaning unless all features can realistically be 0. 9. Prediction. After training and evaluating the model, the next step is to make predictions on unseen data and compare them with actual values to assess how well the model performs in real-world scenarios. Let's start by generating predictions for the test set using Model Predict method. It uses the trained linear regression model to predict medical charges for each observation in the test dataset. Next, create a comparison data frame to visualize and compare actual versus predicted values. This creates a side-by-side table of the true charges and the model's predictions for each patient in the test set. To evaluate these predictions visually, let's create a scatter plot using Seaborn. Each point in the plot represents one patient. If the prediction is perfect, the point will lie exactly on the diagonal line. This part is to add a reference line. This line represents perfect predictions. Points that are close to this line indicate accurate predictions, while points far away suggest prediction errors. Let's look at the graph. The model does a reasonably good job of predicting medical charges overall. In the lower charge range, most points are close to the red line, meaning the model is performing well. However, it underestimates charges for high-cost individuals, which may be due to the nonlinear effects of some features in certain ranges. While the model captures the general relationship well, a more flexible model, like decision trees or ensemble methods, might improve prediction in the high-cost cases. 10. Evaluation. Let's evaluate how well the model performs. Let's start by generating predictions for both the training set and the test set by using the predict method. Next, calculates the MSE, RMSE, and R2 score for both training and test sets like this. Mean squared error measures the average of the squared differences between actual and predicted values. Lower values indicate better performance. Root mean squared error is the square root of MSE. This is easier to interpret than MSE. R2 measures the proportion of variance in the target variable that is explained by the features. It ranges from 0 to 1. A score closer to 1 means better fit. Now let's look at the results. First, it shows a good predictive performance. The model has an R2 of 0.78 on the test set, which means it explains about 78% of the variance in medical charges, a strong result for real-world data. Also, this indicates that the model is doing a good job of capturing the main patterns and relationships in the data. Second, no overfitting. The test RMSE is slightly lower than the train RMSE. It suggests that your model is not overfitting, and may even be generalizing a bit better on the test set. Third, the error magnitude. An RMSE of around 5,800 means the model's predictions are, on average, off by about 5,800. Given the wide range of charges from around 1,000 to 60,000 plus, this is a reasonable error and expected in health cost prediction. If you want to improve performance further, consider using nonlinear models like random forest or XGBoost, or applying a log transformation on charges to reduce skew. 2. Classification overview. Classification is a type of supervised learning used when the goal is to predict class labels. In other words, the model learns to categorize input data into one or more predefined classes based on labeled training data. There are different types of classification tasks. Binary classification deals with two possible classes. Simply can be answered yes or no. Multi-class classification involves three or more possible classes, like classifying multiple animal types. Multi-label classification allows an instance to belong to multiple classes at the same time, like a dog tagged as both dog and pet. Classification can be applied to various data types, including tabular data, images, text data, that's NLP tasks, and categorical data. Several algorithms are commonly used in classification tasks. Logistic regression for linear decision boundaries, decision trees and random forest for nonlinear problems, support vector machines for high-dimensional data, naive Bayes for probabilistic classification, k-nearest neighbors for distance-based classification, neural networks for more complex patterns in image or text data, and XGBoost. To measure how well a classification model performs, we use metrics like accuracy, overall correctness, precision and recall, useful for imbalanced datasets, F1 score, harmonic mean of precision and recall, confusion matrix to visualize true versus predicted classifications. Here is a quick example of evaluation metrics for classification that predicts whether an email is spam or not. Let's say we have a total of 10 emails. 5 of them are spam and 5 are not spam. Also, let's say the model's performance was like this. The model correctly identified 4 spam emails, which are called true positives. It also correctly predicted 3 emails as not spam, which are true negatives. However, the model made 2 mistakes where it incorrectly labeled normal emails as spam. These are false positives. Additionally, the model missed 1 actual spam email and wrongly marked it as not spam, which is a false negative. These 4 values help us understand how accurate and reliable the model's predictions are. Next, let's measure how well the model does using 4 metrics: accuracy, precision, recall, and F1 score. Accuracy shows how many predictions were correct out of all 10 emails. In this case, the model correctly predicted 4 spam emails and 3 not spam emails, which means it got 7 emails right. So the accuracy is 7 out of 10, 70%. This gives us a general idea of how often the model makes correct predictions overall. So this can be said as overall correctness. Precision tells us how reliable the spam predictions are. The model predicted 6 emails as spam, but only 4 of those were actually spam. That means the precision is 4 out of 6, around 67%. So this is known as reliability. Recall tells us how well the model finds actual spam emails. Out of the 5 real spam emails, the model successfully caught 4 of them. That means the recall is 4 out of 5, 80%. This shows that the model is good at detecting spam, though it missed one. So this is known as sensitivity. F1 score is a single number that combines both precision and recall. It balances how many spam emails were caught and how accurate the spam predictions were. In this case, the F1 score is about 73%, which shows the model is performing fairly well in both areas. So this balances precision and recall. This evaluation helps us understand not just how many times the model was right, but how useful and reliable it is in practical situations, like detecting spam emails accurately without making too many mistakes. And here is the confusion matrix, which is a table that helps us understand how well a classification model is performing. It compares the model's predictions to the actual correct answers. Instead of just giving us one number like accuracy, it shows us what the model got right and what it got wrong. And it breaks those results into specific categories. This is especially useful when we want to know the type of mistakes the model is making. In our email spam example, we tested the model with 10 emails. Out of those, 5 were actually spam and 5 were not spam. The confusion matrix helps us organize the results clearly. Let's look at the results again using the confusion matrix. The model correctly predicted 4 spam emails as spam. These are called true positives. It missed 1 spam email and predicted it as not spam. This is a false negative. It wrongly predicted 2 normal emails as spam. These are false positives. It correctly predicted 3 normal emails as not spam. These are true negatives. So in total, the model made 7 correct predictions and 3 incorrect ones. The confusion matrix gives us a clear picture of these outcomes and helps us evaluate not only how often the model is correct, but also what kinds of errors it tends to make. This is very helpful for improving model performance and making better decisions in real-life applications. Let's go back to the overview. Common examples of classification include spam detection in email systems, disease diagnosis from patient data, image classification like identifying dogs versus cats, sentiment analysis of customer reviews. Let's try to work on the actual task in the next section. Classification example 1, Titanic classification. This is an example of classification with tabular data. This project belongs to the classification category of supervised learning. The main goal is to predict whether a passenger survived or not on the Titanic, using features like age, gender, ticket class, and more. The output is binary. The model predicts either survived or not survived. The data for this task comes from the Kaggle Titanic dataset, one of the most popular beginner-friendly datasets in the machine learning community. The dataset is in tabular format, with structured rows and columns representing passenger attributes. We will use logistic regression as the main algorithm. Logistic regression is a simple yet effective method for binary classification problems and serves as a strong baseline. To evaluate the model's effectiveness, we will use classification metrics such as accuracy, the overall correctness of the predictions, precision, the proportion of predicted survivors that were correct. Recall the proportion of actual survivors that were correctly predicted. F1 score, the harmonic mean of precision and recall, especially useful for imbalanced data. We will develop this project using Jupyter Notebook for an interactive step-by-step workflow. The tools involved include Pandas for loading and manipulating the data, scikit-learn for building and evaluating the model, matplotlib for visualizing data distributions and model performance. Also, follow the basic machine learning workflow shown in the upper right. Okay, let's get started. 2. Data collection. Let's download the dataset into your system. To collect the data, visit Kaggle. Go to the competition section and search for Titanic Machine Learning from Disaster. Then navigate to the Data tab. You will find 3 CSV files: Train CSV, Test CSV, and Gender Submission CSV. For this task, we will only use the Train CSV file to build and test our model. So click the Download button to get the only Train CSV. Once you download the data, you'll see these features and target label. The Train CSV file contains information for 891 passengers. Each row represents a passenger, and each column provides a feature or label. Target label is survived, whether the passenger survived or not, 1 or 0. The main features are, for example, P class is a ticket class. 1 is first class, 2 is second class, 3 is third class. Others are sex, age, number of siblings or spouses aboard, number of parents or children aboard, port of embarkation, and more. We will prepare and process these features in the following steps to train a model that predicts survival outcomes. 3. Loading the data. Same as the regression task, import the dataset into your Python environment. You'll see rows and columns with meaningful headers like passenger id, P-class, sex, age, fare, and survived. Make sure the CSV file is uploaded into your file browser before running the pandas method. 4. Exploring the data. The goal is to understand the structure of the dataset. For example, by using the shape method, you can understand how many rows and columns there are. In this case, 891 rows and 12 columns. The columns method shows what each column is called. The info method tells you the data types of each column and whether any values are missing. In this case, age, cabin, and embarked have missing values. The describe method shows stats like mean, min, and max for numeric columns like age, fare, and so on. In addition to that, there are many other insights that can be gained from this step. Value distributions like the frequency of values in categorical columns such as sex, embarked, P-class, outliers and unusual values, relationships between features and the target, like survival rate by gender or class, duplicates or irrelevant columns, like identifying columns like passenger ID, name, ticket, which may not help in prediction, potential feature importance, like noticing which features seem related to the target by looking at patterns. Data quality is like assessing if the dataset is clean, balanced, and ready for modeling. In the next section, let's visualize some data to understand relationships between features and survival on the Titanic. Okay, let's visualize some data. First, survival by sex. This chart compares survival rates between males and females. Females have a significantly higher survival rate, around 75%, compared to males around 19%. So the gender is a very strong predictor, possibly due to the Women and Children First evacuation protocol. Next, survival by passenger class. This bar chart shows survival rates across different passenger classes. First-class passengers have the highest survival rate, around 63%, followed by second class around 47%, and third class have the lowest, around 24%. Passenger class strongly influences survival chances, likely due to cabin location, access to lifeboats, and social status. Next, survival by port of embarkation. This plot shows the survival rate by the port where passengers boarded. C is Cherbourg, Q is Queenstown, S is Southampton. Passengers from Cherbourg have the highest survival rate, while those from Southampton have the lowest. Embarkation port may be indirectly linked to passenger class or socioeconomic status. Next, age distribution by survival. This histogram shows age distributions for survivors and non-survivors. Infants and younger passengers have higher survival rates. Orange color survivors outnumber blue fatalities. Many non-survivors were between ages 20 to 40, so age may influence survival, with children possibly prioritized during rescue. Next, fare distribution. This histogram displays the distribution of fares for survivors and non-survivors. Most passengers paid lower fares, 0 to 50. Survivors are more frequent in the higher fare range. Again, fare shows some predictive value, reinforcing its relationship with class and survival. Lastly, fare distribution by survival. This box plot compares the distribution of fares between passengers who survived and those who did not. Survivors generally paid higher fares. Many non-survivors paid low fares, indicating they were likely in lower classes. Fare might be an important factor in predicting survival, potentially reflecting passenger class and cabin location. Here is the quick summary. From the visualizations, we learned the following key insights. Sex matters a lot. Females had a much higher survival rate than males. Gender is a strong predictor. Class is crucial. First-class passengers had the highest survival rate, while third class had the lowest. Fare is informative. Higher fare-paying passengers tended to survive more, likely due to better cabin access and resources. Age has an influence. Young children had relatively better survival rates, possibly due to rescue priority. Embarkation port shows differences. Passengers from Cherbourg had better survival odds compared to other ports. Outliers exist. Fare and age plots show some outliers, but they may carry important information. These patterns suggest that sex, P-class, fare, age, and embarked are valuable features to include for modeling. Now let's move on to the cleaning step. 5. Cleaning the data. The goal is to fix or remove problems in the data set, such as missing values, duplicates, or inconsistent formats. Also to prepare a clean, consistent, and machine-readable dataset for training the model. For example, check for missing values with isNull and the sum methods. You'll see missing values in age, cabin, and embarked. Let's drop unnecessary columns, including cabin, such as passenger ID, cabin, ticket, name. These columns are removed. Because passenger ID and ticket are irrelevant to the prediction task, cabin has many missing values. This is too incomplete. Name is hard to quantify without additional processing. Dropping them simplifies the dataset and avoids noise during model training. For meaningful data, let's fill in values. The age column have missing values, so they are filled with the median age. The median is preferred here over the mean because it is less affected by outliers and better represents the central tendency of age in the data set. About missing embarked values. A few entries had missing embarked values. These were filled using the most common value in the column. This is a safe and simple approach when missing values are few and the mode is clearly dominant. Now you don't have missing values in irrelevant columns. This process matters because messy data causes errors or poor performance during model training. A clean, consistent dataset ensures your model learns patterns correctly. 6. Encoding the data. The goal is to convert categorical features into numerical values so they can be used by machine learning algorithms, which can only process numbers. Machine learning models don't understand text like male or female. We must convert categories into numbers while preserving their meaning. Let's encode sex and embarked. The sex column contains binary categorical values, male and female. We use label encoding for this, which assigns a numerical label to each category. This method is appropriate because there are only 2 categories and no additional columns are needed. Next, encoding the embarked column. The embarked column contains non-ordinal categorical values, S, C, Q, more than 2 categories. As we learned before, we can use one-hot encoding here, which creates separate binary columns for each category. This creates new binary columns, embarked Q and embarked S. We use drop first true to avoid multicollinearity by dropping one category. Embarked C becomes the reference group. This avoids falsely implying an order or ranking between ports. Now, the model can interpret the values numerically for both sex and embarked. In some environments like Jupyter Light, when printing to the notebook directly, the output of pandas get dummies might be formatted as Boolean values, true or false, for display, even though the underlying data is actually numeric, 0 and 1. This is purely a display issue, not a problem with the data. Here is the quick summary of common encoding methods used to convert categorical data into numbers. Label encoding is best for binary categories like male and female, or ordinal ones that have a natural order such as low, medium, and high. It assigns numbers like 0, 1, 2 based on that order. Category codes are a quick way to turn categories into numbers. It works for ordinal or even non-ordinal multi-class categories, but be careful. Models might think there's an order when there isn't. One-hot encoding is ideal for non-ordinal multi-class categories like port names or colors. It creates separate columns with 0 or 1 to indicate the presence of each category without implying any order. Seven, feature selection. In this step, you'll separate the dataset into 2 parts. Features, the input values the model will use to learn patterns. And target, the value you want the model to predict. This step matters because your model learns from features to predict the target, so choosing the right features is critical for accuracy. To select the most relevant features for predicting medical charges, we used a combination of domain knowledge, correlation analysis, and visualization. Based on what we know about the Titanic disaster, we can assume that certain features are likely important, such as women and children were more likely to be rescued. Higher class passengers had better access to lifeboats. Younger passengers may have had higher priority. Fare may reflect socioeconomic status and cabin location. Embarked might indicate regional differences in passenger demographics or cabin assignment. Family connections such as siblings, spouses, and parents' children may influence survival, and so on. To support this, let's check the correlation. This helps find which numerical variables have the strongest linear relationship with the target. This result says sex, P-class, and fare have a notable correlation with survival. Next, visualization. From the earlier visualization, We know higher survival among females, first-class passengers, and those who paid higher fares. Survival rates varied across embarkation ports. Children had slightly higher survival rates. Based on these insights, let's keep all remaining features after cleaning and encoding. X now contains all the features for prediction, and Y contains the target label, survived. 8. Data split. This step is the same as the regression task. The goal is to separate your dataset into different parts so you can train the model on one set and evaluate it on another set, test or validation data. This prevents overfitting and gives a realistic estimate of performance. Typical training set size is 70 to 80%. Test set is 20 to 30%. This time the test size is 0.2 means 20%. 9. Training. The goal of this step is to train data to teach the model how to learn patterns and predict outcomes. First, import logistic regression, a commonly used classification algorithm from scikit-learn. It's ideal for binary classification problems like this one. Next, create an instance of the logistic regression model. Max iterations 1000 inches sets the maximum number of iterations for the solver to converge, useful if the default 100 is too low for convergence. Then train the model using the fit method and the training data. The model learns the relationships between the features and the survived label. At this point, the model has been trained and is ready to make predictions on unseen data. 10. Prediction. The goal is to use your trained model to predict whether new or unseen passengers survived or not. Okay, let's predict on the test set. Once you've trained your model using model fit, you can now use it to predict on X test. This will output an array like this. Each value corresponds to the model's guess. 0 means did not survive. 1 is survived, but for now we don't know if it's correct. Next, let's evaluate the model. 11. Evaluation. The goal is to use evaluation metrics to measure how accurate and reliable your model's predictions are on the test set. Now we are seeing 3 evaluation metrics: accuracy score, classification report, and confusion matrix. Accuracy tells the overall percentage of correct predictions. The classification report provides precision, recall, and F1 score for each class. Precision measures, out of the predicted survivors, how many were correct. Recall measures, out of all actual survivors, how many did the model catch. F1 score tells the balance between precision and recall. In the classification report, support is the number of samples. Macro average is the unweighted average of precision, recall, and F1 score across all classes. It treats all classes equally, regardless of how many samples they have. Useful when you want to know how the model performs per class without bias toward larger groups. Weighted average is the average of metrics weighted by the number of support, meaning the number of samples in each class. It accounts for class imbalance by giving more importance to the larger class. It's more reflective of overall performance when the classes are imbalanced. The confusion matrix shows the number of correct and incorrect predictions made by the model, broken down by actual class and predicted class. Here's the quick summary of those metrics. Okay, let's check each result. From the result of accuracy, the model achieved an accuracy of approximately 81%, meaning it correctly predicted whether a passenger survived or not in 81 out of every 100 cases. This is a good result for a baseline model like logistic regression. The classification report provides more detailed insights. For passengers who did not survive, class 0, the model has precision of 0.83, meaning 83% of the time when it predicted did not survive, it was correct. Recall of 0.86, meaning it correctly identified 86% of the actual non-survivors. F1 score of 0.84, indicating strong overall performance for this group. For passengers who did survive Class 1, the model has precision of 0.79, meaning 79% of the predicted survivors were correct. Recall of 0.74, meaning it caught 74% of the actual survivors. F1 score of 0.76, showing reasonable but slightly weaker performance compared to Class 0. Overall, the model performs better at identifying non-survivors than survivors, but the difference is not extreme. Next, the confusion matrix. This is the visualized confusion matrix. 90 passengers were correctly predicted as not surviving. 55 passengers were correctly predicted as surviving. 15 passengers were wrongly predicted as survivors. They actually did not survive. 19 passengers were wrongly predicted as non-survivors. They actually survived. This balanced performance across classes suggests that the model is quite effective, although slightly more conservative in predicting survival. The evaluation shows that logistic regression provides a solid starting point for the Titanic classification task. With an 81% accuracy and well-balanced precision, recall, and F1 scores, the model is able to make reasonable predictions. Future improvements could include trying more complex models like random forest or XGBoost to potentially boost performance further. Let's move on to another classification task which uses image data. Handwritten digit classification. This project falls under the classification category of supervised learning, where the goal is to classify handwritten digits 0 to 9 based on pixel values in small grayscale images. The dataset comes from Ski-Learn's built-in digit recognition dataset, which contains 8 by 8 pixel images of handwritten digits. Each image represents a number from 0 to 9 and is labeled accordingly. The data type here is image-based, as each input is a matrix of pixel values. Also, the pixel values range from 0 to 16. You can check the details about this dataset on sklearn's website like this. This task is framed as a multi-class classification task because there are 10 possible digit classes, 0 through 9. To solve this problem, we use convolutional neural networks, which are well suited for image recognition tasks. CNNs can automatically learn spatial hierarchies of features and patterns within the image, making them ideal for recognizing digits from raw pixel inputs. The performance of the model is evaluated using several metrics. Accuracy shows the overall correctness of predictions. Precision, recall, and F1 score give more detailed insight into how well the model performs on each digit class. A confusion matrix is also used to visually understand which digits are being confused with others. The project is implemented in Jupyter Notebook using tools such as TensorFlow and Keras for building and training the CNN, and Matplotlib for visualizing samples and performance results. Also, we will follow the basic machine learning workflow shown in the upper right. Okay, let's get started. 2. Loading the data. The goal is to import the dataset, which contains images of handwritten digits and their corresponding labels, 0 to 9. First, import load digits from the sklearn datasets. Next, load the digits dataset into a variable called digits. It contains both the image data as flattened arrays and the corresponding labels that are the correct digits. Then extract the features and target labels separately. Three, exploring the data. The goal is to understand the shape, structure, and variety of the images and labels in the dataset. Let's visualize sample images. This example is visualizing the first 5-digit images. It creates a new figure. It's like a canvas to draw on, with a custom size of 10 units wide and 2 units tall. This ensures the images are displayed clearly in a horizontal row. Next, loops through the first 5 images in the dataset, indices 0 to 4. Then create a subplot inside the figure. That part means 1 row, 5 columns, and I+1 subplot. This lets you display 5 images side by side in a single row. The image show displays the ith image using grayscale color, black to white. Image's I is an 8 by 8 matrix of pixel brightness values. Also, add a small title above each image showing its true label. Axis off hides the axis ticks and grid lines to make the images look cleaner. Finally displays the complete plot with the 5-digit images and their labels. Now you'll see 5 handwritten digit images in a row, each labeled with the digit it represents. This helps you visually confirm that the dataset is correctly loaded and labeled. 4. Pre-processing. The goal is to prepare the image data for a convolutional neural network. It expects the input image shape to have a specific 3D shape, number of images, height and width of each image, and number of channels. And the label shape needs to be one-hot encoded. Also, CNN expects the normalized pixel values to help the model learn faster and more accurately. We scale them to a 0 to 1 range. Let's reshape the input first. -1 means figure out the number of samples automatically. 28 means the height and width of each image. The last one means the number of channels. It's 1 because this is grayscale. Next, reshape labels. Convert the digit labels into a format that a CNN can understand for classification called one-hot encoding. First, import the toCategorical function from TensorFlow Keras. It's used to convert class labels into one-hot encoded vectors. So the result is that each label is transformed from a single number to a vector like this. For the input x, normalize it divide by 16 because the pixel values range from 0 to 16 according to the sklearn website. Then split the data. This step is the same as the other tasks. Five, training model. The goal is to build a CNN that can learn patterns from image pixels and correctly classify digits, 0 to 9. First, import the required modules. Sequential is a linear stack of layers. Conv2D is a convolutional layer that detects features in images. Max pooling 2D reduces image size to make learning faster and reduce overfitting. Flatten turns 2D image data into 1D before passing to dense layers. Dense is fully connected layers, like traditional neural networks. Next, build the CNN model. This means the first layer is 16 filters, 3 by 3 kernel size. ReLU activation introduces nonlinearity. The input shape tells the model that the input is an 8 by 8 grayscale image. Max pooling reduces each 2 by 2 block to its max value, then downsamples the image by half. The flatten method flattens the 2D feature maps into a 1D vector to connect to the dense layer. The first dense method creates a fully connected hidden layer with 64 units and ReLU activation. The last dense method outputs a layer with 10 units, 1 for each digit, 0 to 9. The softmax activation turns outputs into probabilities that sum to 1. Next, compile the model. Optimizer Atom automatically adjusts learning rate. Lost categorical cross-entropy is used for multi-class classification with one-hot encoded labels. Metrics accuracy tracks classification accuracy during training. Finally, train the model. Trains the model for 20 epochs and uses 32 samples per batch. This means the model will go through the entire training dataset 20 times. Each full pass is called an epoch. More epochs can help the model learn better, but too many might lead to overfitting, where it memorizes the data instead of learning patterns. The batch size 32 inches means the model will look at 32 samples at a time before updating its internal weights. The training data is divided into small chunks of 32. A smaller batch size uses less memory but might be slower. A larger batch size can be faster but may not generalize well. So common sizes are 32, 64, and 128. and 20% of the training data is held out for validation to monitor how well the model generalizes during training. History stores training and validation accuracy and loss over time. Six, prediction. The goal is to use the trained model to predict which digit appears in each image from the test set. Okay, let's predict classes on the test set. This will give you an array of probabilities for each digit. For example, let's check the probabilities for a specific image. The image and each prediction for that image look like this. It says the model is confident, it's a 6. But this shows all the probabilities for one image, so it's a little hard to understand. So let's change it to only return the class label with the highest probability. To convert probabilities to class labels, we can use argmax method to find the index of the highest probability in each prediction. Okay, let's print out predicted labels and true labels. Now you have actual class predictions. As we checked, the predicted first class label is 6. And it matches the real class labels. The other predictions also seem to match the actual class labels. Next, let's evaluate the model. 7. Evaluation. The goal is to build a CNN that can learn patterns from image pixels and correctly classify digits, 0 to 9. Okay, let's create a classification report that shows detailed metrics. It includes accuracy, precision, recall, and F1 score. Accuracy is an overall percent of correct predictions. Precision tells how many predicted digits were correct. Recall tells how many actual digits were correctly identified. F1 score balances between precision and recall. In addition, support is the number of samples in the test set for each class. Macro average means that the unweighted average across all classes. So each class is treated equally even if it's rare. Weighted average means that the average weighted by support. So it's more realistic for imbalanced datasets. Common classes have more influence. Alright, let's have a look at the result briefly. The model achieved an overall accuracy of 96% on the test set, which means it's correctly predicting 96 out of every 100 digits. Most digit classes like 0, 2, 3, 4, 5, 6, and 7 were predicted perfectly or nearly perfectly with F1 scores close to 1, meaning both precision and recall were very high. Digit 1 had a slightly lower precision, 0.84, but high recall, 0.93, meaning the model often correctly identifies ones but sometimes mistakenly labels other digits as 1. Digit 8 had the weakest performance, with a recall of 0.77 indicating that the model missed some true 8s, though precision was still perfect at 1.00. The macro average and weighted average are both 0.95 to 0.96, confirming consistent and strong performance across all digit classes. Next, let's check the details with the confusion matrix. It shows exactly where the model got confused between digits. For example, digit 8 is the weakest, often confused with 1 and 9, which may look visually similar in 8 by 8 pixels. You could improve the recognition of 8 by adding more training data for 8, using a deeper CNN or data augmentation, and examining pixel patterns where misclassifications occur. Overall, the model is highly accurate with only minor confusion between digits. 8. Visualization. The goal is to display some test images alongside the model's predicted labels and the true labels, so you can spot correct and incorrect predictions visually. Let's plot 10 test images with predictions. First, creates a new figure or canvas to plot the images. Figure size sets the width to 12 and the height to 4 in inches. Next, loops through the first 10 images in the test set. Each loop will create one subplot for one image. It divides the figure into a 2-row, 5-column grid. I+1 places each image in its respective subplot position, since subplot index starts from 1. The image show displays the test image using grayscale color. The reshape converts the 1D input back to its 8x8 pixel format. CMAP makes the image black and white. Then add a title above each image, including the true label and the predicted label from the model. The axis off hides axis ticks and labels to keep the view clean and focused on the image. Then adds a main title, adjusts the layout, and displays the result. Now you can see the 2x5 grid of images. Each image shows what digit it is and what the model guessed. Looks like the model predicts all the numbers perfectly in this sample. Okay, that's it for this project. Overall, the model achieved an accuracy of 96% on the test set. Most digit classes were predicted perfectly or nearly perfectly, with F1 scores close to 1, meaning both precision and recall were very high. However, we did notice some areas for improvement. Digit 1 had slightly lower precision, meaning the model sometimes mislabeled other digits as 1, even though it was usually good at detecting actual 1. Digit 8 had the weakest performance, with a recall of 0.77, indicating that the model missed some true 8, though precision was still perfect at 1. For further improvement, we can think of several ideas, such as adding more training data and using data augmentation techniques. Also, we can try a deeper CNN and examine pixel patterns where misclassifications occur. Let's move on to another classification task which uses text data. Twitter sentiment analysis. This project is a classification task and a classic example of natural language processing, NLP, which focuses on enabling machines to understand and interpret human language. The main objective here is to predict the sentiment expressed in tweets, whether they are positive, negative, or neutral like this. The dataset used is the Twitter sentiment dataset from Kaggle, which contains thousands of tweets labeled with corresponding sentiments. The data type is text, meaning each input is a piece of unstructured natural language that needs to be converted into numerical form before modeling. This task is framed as a multi-class classification problem, since tweets can belong to more than 2 sentiment categories. The primary algorithm used is logistic regression, a strong baseline model for text classification. It's effective, easy to interpret, and works well with feature vectors generated from textual data. To evaluate model performance, we use standard classification metrics, accuracy to measure overall prediction correctness, precision recall, and F1 score to evaluate performance on individual sentiment classes, especially important if the dataset is imbalanced. This NLP project is developed using Jupyter Notebook, and the following tools are used. Pandas for data loading and manipulation, scikit-learn for modeling and evaluation. TF-IDF vectorizer means term frequency inverse document frequency. This is for converting text data into numerical feature vectors. And we'll follow the basic machine learning workflow as shown in the upper right. Okay, let's dive in. 2. Data collection. Let's download the dataset into your system. To collect the data, visit Kaggle. Go to the dataset section and search for Twitter sentiment analysis. Then click the download button to get the dataset. Once you download the data, you'll see 2 files. This time we will use only the training CSV file. Once you open the file, you'll see these features and the target label. It does not include column headers, which means we need to assign them manually when loading the data. The target label is sentiment, whether the user is positive, negative, or neutral. 3. Loading the data. The goal of this step is to import the dataset into our Python environment so we can work with it using data analysis tools. Since the dataset has no column headers, we also need to assign meaningful column names manually. To assign column names, you can write like this. Then you'll see the data table like this. Let's move on to the next step. 4. Exploring the data. The goal of exploring the data is to understand its structure, size, and quality. We want to identify patterns, check for any unusual values, and get a sense like how many tweets there are, what the sentiment distribution looks like, if there are missing values or duplicates, the average length of tweets, examples of each sentiment, and so on. Let's explore some data. For example, the info method tells us about the structure and completeness of the dataset. The dataset contains 74,681 rows and 4 columns. The ID column is an integer and has no missing values. The topic, sentiment, and text columns are of type object. The text column has 73,995 non-null entries, meaning some of them are missing text. From the sentiment value counts, this shows the number of tweets labeled with each sentiment: negative 22,542 tweets, positive 20,831 tweets, neutral 18,318 tweets, and irrelevant 12,990 tweets. According to the Kaggle description, irrelevant should not be treated as a fourth class. Instead, we should relabel all irrelevant entries as neutral later, so the dataset only has 3 valid classes. Isnal sum shows the number of missing values in each column. Only the text column has missing values, 686 rows. All other columns are complete. We'll likely need to remove these rows in the cleaning step since a tweet without text cannot be analyzed for sentiment. Duplicated sum reveals that 2,700 rows are exact duplicates. These duplicates should be removed to avoid biasing the model with repeated examples. Now we briefly understand the dataset. Let's move on to the next step. 5. Cleaning. The goal of data cleaning is to remove or fix data that is incomplete, duplicated, or not useful. This ensures that the dataset is clean and reliable before feeding it into a machine learning model. From the exploration step, we discovered that the dataset contains 3 key issues: missing values in the text column, specifically 686 tweets without any content. Duplicate rows, a total of 2,700 rows, are exact duplicates. Irrelevant sentiment labels, 12,990 tweets are labeled as irrelevant, which are not valid according to the official definition. To clean the data, first drop all rows where the tweet text is missing with drop_NA method, since tweets with no content cannot be used for sentiment analysis. Next, we remove all duplicate rows with drop_duplicate method to ensure that the model does not see repeated data, which could introduce bias. Finally, based on the Kaggle description, we replace all irrelevant sentiment labels with neutral using the replace method. After cleaning, all rows now contain valid tweet text. All duplicates are removed. Sentiment labels are now standardized to 3 classes only: positive, negative, and neutral. This prepares the data set for the next step, pre-processing, where we will transform the text data into a format suitable for machine learning models. Another essential part of the cleaning step is cleaning the text, especially for NLP tasks like sentiment analysis. The goal is to fix unclean text, such as URLs, hashtags, and symbols. Let's create a function called cleanText to normalize and clean the raw tweet content. The function first checks whether the input text is a valid string using the isInstance method. If not, it returns an empty string to avoid errors when processing non-text data. The lower method transforms all characters to lowercase. This ensures that words are treated the same, reducing unnecessary variation. Other methods use regular expressions. The first one is to remove URLs. URLs typically don't carry sentiment and can be distracting. The next one is to remove mentions such as that username. These don't affect the sentiment directly and can be treated as noise. The next one is for removing hashtags. While hashtags may indicate sentiment, they're removed here for simplicity and to avoid sparse text. The next one is for removing punctuation. This helps focus on the words themselves, although some models may handle punctuation meaningfully. The next one is to remove numbers. In many sentiment analysis cases, numbers don't add much value. The last one is to remove extra spaces. It collapses multiple spaces into one and trims leading and trailing white space. This results in clean and consistent spacing between words. Then return the clean text. Let's apply this function to the original tweet column and creates a new column called clean text, which stores the pre-processed version of each tweet. Now you'll see the clean text. For example, numbers are removed, text is converted to lowercase, and punctuation marks are eliminated. After all cleaning steps, the processed text is returned for use in further steps like vectorization and model training. 6. Preprocessing. The goal of preprocessing is to convert the clean text and labels into numerical formats that can be used by machine learning models. This involves splitting the dataset, transforming the text into numeric features, and encoding the sentiment labels. First, data split. Before vectorizing the text, we split the dataset into training and testing sets. X contains the clean tweet text. Y contains the sentiment labels. We split 80% of the data into the training set and 20% into the test set. Setting random state ensures reproducibility. We do this before vectorization because we need X text test untouched for the final prediction step. Later, we will compare true sentiment with predicted sentiment with X text test, which is the text data before vectorization, like this. Next, vectorization. We convert the training and testing text data into numeric features using TF-IDF, term frequency inverse document frequency. TF-IDF vectorizer transforms words into numerical vectors based on how important a word is in a document relative to the entire dataset. The max features 5,000 inches limits the feature space to the top 5,000 words by importance. The fit transform learns the vocabulary from the training data and transforms it. The transform method applies the same transformation to the test data. The difference between fit transform and transform is that fit transform method learns the pattern from the input data and then transforms the data into numerical features, all in one step. It's used only on the training data because this is where the model learns the vocabulary. On the other hand, the transform method only transforms the input data based on what was learned earlier using fit. It does not learn anything new. You use it on the test data to ensure the model processes it the same way as the training data. So using fit transform on the test data would be a mistake because it would introduce information leakage from the test set into the training process. After the vectorization, the output looks like this. The output is in sparse matrix format. Each line follows row index, column index, and value format. The vectorizer has learned a vocabulary of 5,000 words, as set by max features 5,000. Each tweet becomes a 5,000 inches dimensional vector, where most values are 0 because a tweet is short. Non-zero values represent words that appear in the tweet, and their value shows how important the word is in that tweet relative to the dataset. For example, words like borders from the tweet probably correspond to some of those column indices. Next, encoding labels. Finally, we convert the target labels from strings to integers using label encoding. Label encoder assigns a unique integer to each class label. For example, negative is 0, neutral is 1, positive is 2. This step is essential because most machine learning models require numeric target values. After preprocessing, you have xtrain and xtest as numeric feature matrices from TF-IDF. You have ytrain and a ytest as encoded numeric labels. The data is now fully prepared for model training. 7. Training. The goal of this step is to train a machine learning model using the preprocessed data. The model will learn to recognize patterns in the training data that associate tweet content with sentiment labels. Let's use logistic regression as a model. Logistic regression is a simple but powerful classifier that works well for many text classification problems. Despite its name, it is commonly used for classification tasks, not regression. It finds the best boundary between classes based on the input features TF-IDF values. Max iterations 1000 inches sets the maximum number of iterations the model will try while optimizing. TF-IDF often results in high-dimensional data, so a higher limit like 1000 ensures convergence. Then trains the model using X-train, which is feature vectors for tweets, and Y-train, which is sentiment labels encoded as integers. During training, the model learns which patterns of words are most likely to correspond to each sentiment class. The model is now trained and ready to make predictions on unseen data. It can classify new tweets into positive, negative, or neutral based on their content. Eight, prediction. The goal of this step is to use the trained model to predict the sentiment labels for the unseen test data. These predictions will later be compared with the actual labels to evaluate model performance. The model predict takes the TF-IDF transform test data and outputs the predicted sentiment labels. These predictions can now be compared to the true labels. At first glance, it seems like the model predicts the label accurately. Let's move on to the evaluation step to measure how well the model performed. 9. Evaluation. The goal of this step is to measure how well the model performed on the test data using common evaluation metrics like accuracy, precision, recall, F1 score, and the confusion matrix. First, accuracy score. Accuracy is the percentage of correct predictions out of all predictions. In this case, the model correctly predicted the sentiment for about 72.5% of the tweets in the test set. This is a good baseline for a 3-class classification task. From the classification report, the model performs reasonably well with balanced metrics across all 3 classes. Let's look at just a few highlights. The model is strong at identifying negative and neutral tweets, but slightly weaker for positive. For example, for negative tweets, 77% of the predictions are correct. Neutral tweets are predicted correctly in 77% of the recalls. For positive tweets, a 65% lower recall means it misses more actual positive tweets. From the confusion matrix, we can know the number of correct and incorrect predictions for each class. This is the visualized confusion matrix. Let's look at some highlights. The model performs best at classifying neutral tweets, correctly predicting 4,624 neutral tweets, but predicted 651 of them as negative and 712 as positive. Positive tweets are the most misclassified, especially as neutral, 1050 times. So the confusion mostly occurs between positive and neutral, suggesting the language used in those classes may be more similar or subtle. So these results suggest that this is a balanced and reasonably effective model, with room for improvement, especially in handling positive versus neutral tweets. 10. Visualization. Let's go over the sample comparison between true sentiment and predicted sentiment. This code creates a new data frame named results that compares the actual sentiment labels to the predicted ones. X text test values gives you the original tweet text from the test set. Inverse transform converts the encoded labels back to their original form, like from 0 to negative. The same goes for YPred. It decodes predicted labels. The result sample displays a random sample of 10 rows to visually inspect model performance. Okay, let's check the result. Looks like the model performs well overall, especially for negative and neutral tweets. 8 out of 10 are correct, Most errors come from confusing positive and neutral, which matches the confusion matrix insight. These examples highlight how subtle tone or informal language can challenge the model. That's it for this task. If you want to improve it further, you can focus on boosting recall for positive tweets through more training data or balancing techniques, and exploring other models such as support vector machine, random forest, or fine-tuned BERT. Supervised Learning 3, Computer Vision. Computer vision is a subfield of supervised learning that enables machines to interpret, understand, and make decisions based on visual information, such as images or videos. It focuses on tasks that require a model to extract meaning from visual data and classify or localize objects within that data. Common task types in computer vision include image classification, determining what object or category an entire image belongs to, like identifying animals. Object detection, identifying and locating multiple objects within an image using bounding boxes, like detecting a cat in an image and where it is. Semantic segmentation, classifying each pixel in an image to a category like cat, road, sky. Instance segmentation, it's like a semantic segmentation but distinguishing between different instances of the same object class. In this case, it distinguishes between cats of the same class. Key point detection, locating specific points or landmarks in an image like this. This category works with visual data types, mainly images and videos. These could be medical scans, satellite imagery, security footage, or real-time camera feeds. To perform these tasks, computer vision uses specialized algorithms, primarily based on deep learning, CNN, convolutional neural networks, the backbone of most vision models used for feature extraction from images. RCNN, faster RCNN are object detection models that improve speed and accuracy through region proposals. YOLO, you only look once, and SSD, single shot detector, are fast real-time object detection algorithms. EfficientDet is a scalable and efficient object detection model developed by Google. To evaluate model performance, various metrics are used. Accuracy is the overall correctness of predictions. IOU, intersection over union, measures the overlap between predicted and actual bounding boxes. Mean average precision is a standard metric for object detection quality. Precision, recall, F1 score are especially useful in detection and classification tasks. Pixel accuracy, dice score, used in segmentation tasks to assess how well pixel-level predictions match ground truth. Let's take a closer look at IOU and mean average precision, which are often used in computer vision. First, intersection over union. Let's say there is a photo of a cat with two boxes drawn around it. The blue box is called the ground truth. This shows the correct location of the cat as labeled by a human. The red box is the prediction. This is where the computer model thinks the cat is. Where these two boxes overlap is labeled intersection. This is the part that both the ground truth and the prediction agree on. It means the model correctly found this part of the object. Now, IOU, which stands for intersection over union, is a score that tells us how much the predicted box overlaps with the correct one. It is calculated by dividing the area of the overlap by the total area covered by both boxes combined. If the prediction perfectly matches the ground truth, the IOU will be 100%, meaning it's a perfect prediction. If there is no overlap at all, the IOU will be 0, meaning the prediction is completely wrong. In this example, because the red and blue boxes only partially overlap, the IOU would be somewhere between 0 and 1. This helps us measure how well the object detection model is performing. Next, mean average precision. It is a common metric used to evaluate how well an object detection model performs. It tells us how accurately the model detects objects and how well it avoids false detections. To calculate mean average precision, we first calculate something called average precision for each object class, like cat, dog, or car. Average precision measures how well the model performs across different levels of recall and precision. Once we have the average precision for each class, we average them all together. This final score is called mean average precision. A higher map means the model is better at detecting objects correctly. Mainly two different thresholds of mean average precision are used. Mean average precision 50 is a version of mean average precision where we only count a detection as correct if the IOU is 50% or more. This means that the predicted box needs to overlap with the correct box by at least half to be considered a correct match. This metric is easier to pass, so the score is usually higher. It is often used in many YOLO model benchmarks. Mean average precision 50 to 95 is a more detailed and stricter version of mean average precision. Instead of checking overlap at just one level, like 50%, it calculates the average precision at 10 different IOU thresholds, from 50% to 95% in steps of 5%. Then it averages all these average precision scores. This gives a much more complete picture of how well the model detects objects, not just when it's kind of close, but also when it needs to be very precise. Okay, let's go back to the overview. Common real-world examples of computer vision include classifying handwritten digits, such as recognizing numbers and postal codes, detecting faces in camera feeds or security systems, counting vehicles in traffic videos for transportation analysis, segmenting tumors in medical images to aid diagnosis, real-time object tracking in surveillance or autonomous vehicles. Okay, let's work on one of the computer vision tasks. Vehicle detection. This project falls under the computer vision category of supervised learning. The main goal is to detect and classify vehicles such as cars and trucks in drone footage. This is not just about recognizing what's in an image, but also about locating each object within the image using bounding boxes. We are using a pre-annotated dataset from RoboFlow Universe, specifically the Drone Crossroad Tracking dataset, which includes labeled images taken from aerial drone footage. These labels specify the class of each vehicle and its location in the image, which means bounding box coordinates. This makes it possible to train an object detection model without needing to label the data manually. However, if you have your own images, you can create your own dataset by annotating each image with bounding boxes and class labels using tools like RoboFlow's built-in annotation interface. It gives you the flexibility to build custom models tailored to your specific use case or environment. The task is a classic example of object detection, where the system must not only identify the class of each object, but also determine its position within each frame. To perform this task, we use YOLO V8, a state-of-the-art object detection algorithm known for its speed and accuracy in real-time detection tasks. YOLO V8 is designed to process images and videos efficiently while maintaining high detection accuracy. To evaluate the model's performance, we use metrics specific to object detection, including mean average precision that measures precision across all classes and thresholds. Precision and recall assess the correctness and completeness of predictions. Intersection over union measures how well predicted bounding boxes match the actual ones. We'll develop and train the model in Google Colab, which is particularly suitable for this kind of computation-heavy task. Colab provides free access to GPUs, which significantly speeds up training and allows even resource-intensive models like YOLO V8 to be trained without the need for a powerful local machine. Key tools include Ultralytics YOLO library for model training and inference, RoboFlow for downloading, organizing, and preparing the dataset. And we'll follow the workflow as shown in the upper right. Okay, let's dive in. 2. Loading data. The goal is to download the annotated dataset to your environment. First, go to RoboFlow Universe and search for a public dataset called Drone Crossroad Tracking. Once you find it, click to open the project page where you'll see dataset details and class information. Navigate to the Dataset or Versions tab. Then click on the Download Dataset button. If the dataset is not directly downloadable, you may first need to click Fork Project to copy it into your own RoboFlow workspace. When downloading, you will be asked to choose the export format. Select YOLO V8 as the target format for this project. After selecting YOLO V8, RoboFlow will generate a custom download script for your chosen dataset. Copy that script and paste it into your coding notebook. In this example, we're using Google Collaboratory, so you can run the script directly in a cell. Once the script runs successfully, you'll see folders like train, valid, and test, each containing images and labels subfolders. You will also get a data YAML file, which YOLO V8 uses to understand your dataset structure. Before training, open the data YAML file and make sure the paths listed for train, valid, and test are correct and match the actual folder structure. 3. Install model. The goal is to install the Ultralytics YOLO V8 library, which allows you to train, validate, and run predictions using a simple Python interface. It's perfect for object detection tasks like vehicle detection. First, install Ultralytics. If you're using Google Collaboratory, before installing anything, it's important to switch your runtime to use a GPU. This will significantly speed up training. At the top menu, go to Runtime and change the runtime type. Under Hardware Accelerator, select GPU, then click Save. Once you've set the runtime to GPU, run this command in a code cell to install Ultralytics. If you're using Jupyter Notebook, you don't need the first exclamation mark. Next, verify the installation. Once installed, import and check the version with this code. You'll see the version of Ultralytics. Then import YOLO. Now you can do loading a pre-trained model, training a custom model, and running predictions or evaluations. YOLO V8 comes in different sizes. You can choose based on your device speed and accuracy needs. This time, we'll use YOLO V8N to focus on the processing speed rather than the accuracy. Now you're ready to train the models. 4. Training the model. The goal is to train YOLO V8 on your labeled vehicle dataset so it can learn to accurately detect and classify objects like cars and trucks using bounding boxes. Let's run this code. This tells YOLO V8 to train a custom object detection model using the dataset and configuration specified. The data tells YOLO where your dataset is located. The data YAML file includes the paths to your training and validation images, the number of classes, NC2, and the list of class names. So it's the link between your data and YOLO V8. The epoch's 50 inches means the model will train for 50 complete passes over your training dataset. You can increase this number later if the model hasn't fully learned. Image size 640 inches resizes all training images to 640 by 640 pixels. It's a standard size that balances accuracy and training speed. Smaller sizes are faster, larger sizes are more detailed but slower. Batch 16 inches means that the model is trained using 16 images per batch. It affects memory usage, so adjust depending on your GPU. If training crashes or is slow, reduce to 8 or 4. After the training, you'll see a folder called Runs with Best PT and Summary Images. The Best PT is your best trained model. So keep this file safe. It's the one you'll use going forward for making predictions and evaluation. Confusion matrix shows class confusion during validation. For example, your model predicted car correctly 939 times. It confused car as background 143 times. This means it missed those vehicles. The results image shows the training and validation metrics. The first 3 in the top row show training losses. Train box loss shows how well bounding boxes are fit, lower is better. Train class loss shows classification error, mislabeling objects. Train DFL loss means distribution focal loss for box precision. All training losses are steadily decreasing, which means learning is progressing well. The first three in the bottom row show validation metrics. They are also going down. Good generalization. Precision shows how many predicted boxes were correct. It's improved to around 0.85. Recall shows how many true objects were found, rising to about 0.85. Mean average precision 50 inches means average precision with IOU 0.5, reaches around 0.86. Mean average precision 50 to 95 inches means stricter mean average precision, IOU 0.5 to 0.95 average, peaks at around 0.54. Val batch 0 pred shows a sample visual output of predictions the model made on the first batch of validation images. It gives you a quick glance at how your model is performing, like are the boxes accurate? So helps you visually identify problems early. 5. Validation. The goal is to measure how well your trained model performs on data it has never seen before. This helps you understand how accurate your model is. Detect overfitting, good training performance but poor generalization, and decide whether your model is ready for real use or needs more training. Let's load your best trained model and makes predictions on each validation image. Then you'll see these metrics in validation folder under the run folder with result images like the training ones. From the result of the metrics, the model was evaluated on a total of 35 validation images, which included 1,147 vehicle instances across all classes. Overall, the model achieved a precision of 90.3%, meaning most of its predictions were correct. Its recall was 81.9%, indicating it successfully detected the majority of real objects. The mean average precision at IOU 0.5 was 88.9%, which shows the model is performing well in terms of detection accuracy. Under stricter evaluation using mean average precision 50 to 95, the score was 55.4%, still reflecting good performance under tighter box matching requirements. When looking at performance by class, for the car class, which had 1,082 instances, the model achieved 88.2% precision, 82.3% recall, and a mean average precision 50 of 89%. Showing that car detection is very reliable. For the truck class, there were only 65 instances, which is a much smaller amount of data. Despite this, the model performed very well with a precision of 92.3%, recall of 81.5%, and a mean average precision 50 of 88.8%. This suggests that even though there were fewer truck examples in the training data, the model learned to detect them effectively, which is a very promising result. 6. Prediction. The goal is to use your trained model to predict bounding boxes and classes for vehicles in new media, images, or videos. This demonstrates the model's real-world application. Let's make predictions on the image in the test folder. YOLO will draw bounding boxes with labels, and the output is saved under the Runs folder. This is one of the images from the prediction. You can show several images using for loop and image and display method like this. The image is a bit hard to see, but it seems like the model detects cars and trucks correctly. Let's do the same thing for the video image. The video image is downloaded from the platform that provides free short videos like Pexels. YOLO V8 processes the video frame by frame. After the process, you can directly show the video in your notebook with this code. If your video output type is AVI, please convert it to MP4 with this code. Looking at the results in the video, it appears that cars and trucks are detected accurately. There seems to be no difference from the validation results. Now that you've successfully trained and validated your YOLO V8 vehicle detection model and tested it on both images and videos, if you'd like to improve performance, consider training the model for more epochs, switching to a larger model like YOLO V8S or YOLO V8M, or balancing your dataset by adding more examples of underrepresented classes like trucks. You can also experiment with better data augmentation using RoboFlow. Next, it's a good idea to test the model on real-world footage, such as dashcam videos, traffic footage, or live webcam streams, to see how well it generalizes outside of the training data. Once you're satisfied with its accuracy, you can export the trained model to formats like OnX, TensorFlow Lite, or TorchScript, depending on your deployment platform. This makes it possible to integrate the model into mobile apps, web applications, or edge devices like Raspberry Pi. 4. Unsupervised learning. 1. Clustering. Clustering is a type of unsupervised learning where the goal is to group similar data points together based on underlying patterns or similarities, without using any labeled outcomes. Unlike supervised learning, clustering algorithms do not know the correct answer in advance. Instead, they try to discover the structure hidden within the data. There are two main types of clustering. Hard clustering, each data point belongs to only one cluster, like k-means. Soft clustering is, a data point can belong to multiple clusters with certain probabilities, like Gaussian mixture models. Clustering can be applied to many types of data, including tabular data, images, and text. Popular algorithms used for clustering include k-means, the most widely used method that partitions data into k distinct groups. Hierarchical clustering builds a hierarchy of clusters using a tree-like structure. DBSCAN groups data based on density, useful for finding arbitrarily shaped clusters. Gaussian mixture models is a probabilistic model that assumes data is generated from a mixture of Gaussian distributions. Agglomerative clustering is a bottom-up approach to hierarchical clustering. To evaluate the quality of clustering, even without labels, we use silhouette score measures how similar an object is to its own cluster compared to other clusters. Davis-Bouldin index evaluates the compactness and separation of clusters. Inertia SSE measures the internal coherence of clusters, used in k-means. Visual methods like 2D or 3D scatter plots or dendrograms, often used to assess separation visually. Some common real-world examples of clustering include grouping customers by purchasing behavior for targeted marketing, organizing news articles by topic, identifying geographic regions based on demographic or satellite data, clustering product reviews by sentiment or theme, grouping genes in biology for research purposes. Okay, let's work on one of the clustering tasks. Unsupervised learning clustering example, customer segmentation. This project falls under the category of unsupervised learning, specifically a technique known as clustering. The main goal is to group customers into different segments based on their purchasing behavior. These segments can then be used for targeted marketing, personalized services, or deeper customer analysis. The dataset comes from Kaggle's Mall Customers dataset, which contains customer details such as age, income, and spending score. The data is in tabular format with structured rows and columns, making it ideal for algorithms like k-means. Since there are no predefined labels in this task, it is handled using unsupervised learning, where the model identifies patterns and natural groupings in the data on its own. The technique used here is k-means clustering, a popular algorithm that divides customers into k distinct clusters based on similarity. To determine the best number of clusters, we use the elbow method. It visually identifies the point at which adding more clusters doesn't significantly improve the fit. The project is implemented using Google Colab. The main tools are pandas for data manipulation, scikit-learn for applying k-means and computing metrics, Matplotlib for visualizing clustering results and decision boundaries. And we'll follow the workflow as shown in the upper right. All right, now let's get started. 2. Data collection. Let's download the dataset into your system. In this example, we use the Kaggle Mall customer segmentation dataset. You can find the dataset from the dataset page on their platform and download it as a CSV file. It looks like this. You'll see the features such as customer ID, gender, age, annual income, and spending score. Let's load this dataset into your coding environment. 3. Loading the dataset. Let's read the dataset into a data frame using pandas, same as the other tasks. Now you can see the first 5 rows. Let's take a closer look at the data in the next step. 4. Exploring the data. The goal of this step is to get a clear understanding of the dataset structure and contents, identify any obvious issues, and gain insights through initial visualizations. First, the info method says the dataset has 200 rows and 5 columns. There are no missing values in any column. Each has 200 non-null entries. The data types are customer ID, age, annual income, and spending score are all integers. Only gender is an object type. Next, describe method says gender is a categorical column with 2 unique values. The most common is female, which appears 112 times. Customers are between 18 and 70 years old. The average age is around 38 years. Annual income ranges from 15K to 137K, with an average of 60.56K. The standard deviation is about 26.26K. Spending score ranges from 1 to 99 with an average of 50.2. This score was likely assigned by the mall based on customer behavior. Let's visually explore the distributions and relationships of the key features: age, annual income, and spending score. First, histograms with KDE. Those 3 main numerical features are plotted with this code. First, create a main canvas and plot 3 subplots using a for loop. KDE True adds a kernel density estimation line to show the distribution shape. Bins 20 defines the number of bars or intervals in each histogram. From these graphs, we can see that most customers are in their 20s to 40s, peaking around age 35. The number of older customers drops off, but they are still present. The age range is wide, showing good diversity for age-based analysis. From the distribution of annual income, most customers earn between 40K and 80K annually. The distribution is right-skewed, meaning there are fewer high-income customers. The peak appears around 60K to 70K, which could be the most common income segment. From the distribution of spending score, the spending scores range across the full scale from 1 to 100, indicating diverse spending habits. The distribution is like multimodal, showing noticeable peaks around 40 to 60 and again near 80. This suggests there may be distinct groups of spenders, low, average, and high. Next, box plots. Box plots show median quartiles and any potential outliers. The code is almost the same as the histograms. Just replace the histplot method with the boxplot method. Let's look at the graphs. There is one noticeable outlier above 130K in annual income. This means while most customers fall into a normal income range, a few have exceptionally high income. These can be treated separately or normalized depending on modeling needs. Next, pair plot. The code looks like this. This time, the pair plot method is used. Let's look at the graph. There's no strong linear relationship, but we can visually spot clusters, especially in annual income versus spending score. Largely 5 clusters, possible groupings like high-income low spenders and low-income high spenders, and so on. This plot gives an early clue that k-means clustering will work well. 5. Cleaning the dataset. The goal is to ensure the dataset is clean and reliable for clustering by handling missing values or duplicates and identifying and addressing outliers if necessary. As we know from the exploration step, there are no missing values. Also, there are no duplicate rows. Next, outliers. From the exploration step, annual income has one mild outlier, but since it's valid, not an error, we'll keep it for now. 6. Feature selection. The goal is to choose the most relevant features, columns, that will be used for clustering. The right features help the model group similar customers effectively. Let's use common methods. From the domain knowledge, age may affect preferences and spending. Annual income indicates purchasing power. Spending score directly shows spending behavior. And gender might be relevant if targeting marketing by gender. Customer ID is just an identifier, not meaningful. Next, let's check the correlations between features. It helps spot redundancy. If two features are very similar, you can drop one. But at a glance, it seems there is no strong correlation between these three, which means each feature provides different independent information for clustering. That helps the algorithm find better separation. From the visualization result of the exploration, we saw a clear variation and distribution in age, income, and spending score, and natural clustering is visible in 2D plots. That confirms they are good candidates. So based on these results, let's use these 4 features. Seven, preprocessing. To prepare the dataset for k-means clustering by converting categorical variables to numerical form and scaling all features so they contribute equally to the clustering algorithm. First, label encoding for gender. In this case, we use label encoding with the map method. This replaces female with 0 and male with 1. This is suitable because gender is a binary categorical variable and mapping keeps the result clean and compact with just one column. Next, feature scaling. Since k-means clustering relies on Euclidean distance, it's important that all features are on the same scale. Without scaling, a feature like annual income, ranging from 15 to 137, could dominate others like gender, just 0 or 1. Let's use standard scaler to standardize the features so they have a mean of 0 and a standard deviation of 1. Now all features are normalized, making the clustering fair and balanced. Let's move on to the modeling step. 8. Modeling. To apply the k-means algorithm to the preprocessed customer data and group similar customers into distinct clusters based on their behavior and characteristics. But before we run k-means, we need to decide on the number of clusters k. There are several ways to decide the number of clusters k, such as elbow method and the silhouette score. Let's try the elbow method. It runs k-means for a range of k values, like 1 to 10. Then calculate the inertia for each k. Inertia is the sum of squared distances from each point to its assigned cluster center. After that, plot inertia versus k. Then look for the elbow point. This is the result. The curve drops sharply from 1 to 4, then begins to flatten around 5. It may be a bit difficult to find, but we can see a change in angle around number 5. From 5 onwards, the gain in clustering performance becomes smaller and smaller. So this point, where the curve bends or elbows, represents the optimal number of clusters. So according to the elbow method, the optimal number of clusters is likely 5. This is where the rate of decrease in inertia slows down, meaning that adding more clusters beyond this point gives diminishing returns in clustering performance. Therefore, we will proceed with K5 for the k-means clustering model. Let's group customers into 5 distinct clusters based on their age, income, spending behavior, and gender. This code fits the k-means model to the scale data. Assigns each customer to one of the 5 clusters. Also, a new column cluster is added to the data frame, representing each customer's cluster assignment. Now let's check the data table, and each customer is labeled as belonging to cluster 0, 1, 2, 3, or 4. We can analyze or visualize each group to understand the shared characteristics within them. Nine, evaluation. The goal is to understand and interpret the clusters created by k-means by visualizing them in 2D space and analyzing the customer characteristics in each group. Let's plot annual income versus spending score colored by cluster. We can use a scatter plot. Please adjust the palette, marker size, and transparency as you like. As you can see, the clustering has effectively segmented customers into 5 meaningful groups. There are clear distinctions, especially between those who have high income but spend differently and those with low income who spend actively. This information can be used to tailor marketing strategies, product recommendations, or loyalty programs for each customer segment. Ten, labeling. The goal is to analyze each cluster and give it a descriptive label based on customer behavior. This helps businesses easily understand and act on the segmentation. Let's check the cluster averages per cluster using the group by method. This helps identify patterns like, are they young or older? Do they earn a lot or a little? Are they high or low spenders? What's the gender ratio? Okay, let's check each cluster. First, cluster 0. This group is the oldest on average, 56 years old, with low income, around 46K, and moderate to low spending. Gender is balanced, about 49% male, so they can be labeled as careful budgeters. Next, cluster 1. These are high income earners, around 85K, with very low spending scores, around 14. All are male, so they can be labeled as wealthy minimalists. Next, cluster 2. This group is young, around 29, earns a moderate income, around 61K, and has a very high spending score, around 70. All are male, so they can be labeled as active shoppers. Next, cluster 3. These customers are mid-aged, around 38, have higher income, around 82K, and above average spending, around 54. All are female, so they can be labeled as premium customers with a female skew. Lastly, cluster 4. This group is the youngest, around 27, earns the lowest income, around 39K, but has a high spending score, around 56. All are female, so they can be labeled as young impulsive spenders. This is the summary table. Let's imagine labeled users. Cluster 0 is a careful budgeters, like a housewife in her 50s or 60s who carefully manages household expenses. She compares prices, uses coupons, and only shops when there's a sale. Practical, steady, and avoids impulse buys. Cluster 1 is wealthy minimalists, like a successful male executive who earns a lot but lives simply. He buys high-quality essentials and avoids flashy or trendy items. Doesn't shop often, only when necessary, and prefers quiet premium brands. Cluster 2 is active shoppers, like a young man in his 20s working in tech or media, who loves sneakers, gaming gear, and online shopping. He spends freely on what he enjoys, fashion, gadgets, and social experiences. Cluster 3 is premium customers, like a professional woman in her 30s or 40s who loves luxury skincare, stylish outfits, and nice restaurants. She has a good income and invests in quality and comfort, loyal to trusted high-end brands. Cluster 4 is young impulsive spenders like a university student or young office worker, very active on Instagram, always shopping online for the latest fashion or beauty products. She loves trying trends and reacts quickly to influencer promotions or sales. This is a simple example. Try creating your own clusters and analyzing them, then let's create your own customer personas. So that's it for this customer segmentation. After evaluating the clustering results, we assign descriptive labels to each group based on average income, spending behavior, age, and gender. These segments help us better understand our customers and make informed decisions for targeted marketing, promotions, or service customization. 5. Reinforcement learning. Reinforcement learning is a type of machine learning where an agent learns by interacting with an environment. Instead of being trained with labeled data, the agent receives feedback in the form of rewards or penalties depending on its actions. Over time, it learns to take better actions to maximize its cumulative reward. This learning process is centered around three key components. State, the current situation the agent observes from the environment, like XYZ position. Action, the decision or move the agent takes, like left and right. Reward, the feedback signal received after taking an action, positive for good actions, negative for bad ones. Typical task types include goal-oriented decision-making, like reaching a destination or winning a game. Sequential decision processes, where decisions are made step by step over time. Balancing exploration and exploitation, trying new actions versus using known good ones. The data in reinforcement learning is dynamic and comes from the environment. It includes the environment states the agent observes, actions the agent takes, rewards it receives in response to those actions. Common algorithms in reinforcement learning include Q-learning and SASA, value-based methods for learning action values. Deep Q networks, DQN, combines Q-learning with deep learning to handle high-dimensional input like images. Policy gradient methods directly learn the policy like the agent's behavior. Actor critic and proximal policy optimization are advanced techniques that combine value-based and policy-based learning to evaluate how well an agent is learning. We use total cumulative reward, the total points collected over an episode. The average reward per episode is the overall trend of improvement. Learning speed is how quickly the agent improves. Policy stability, how consistently the agent makes good decisions. Real-world and simulated examples include training AI agents to play games like chess, Go, or cartpole, robot navigation where agents learn to walk or manipulate objects, stock trading bots that learn to buy and sell profitably, self-driving cars that make safe driving decisions, and smart energy systems that adjust power usage based on demand. Now let's move on to the sample task. Reinforcement learning example. Cartpole reinforcement learning. Here's the overview of this project. This project is a classic example of reinforcement learning, where the goal is to train an agent to balance a pole on a moving cart. Unlike supervised learning, the agent does not learn from labeled data. Instead, it learns through trial and error by interacting with an environment and receiving rewards or penalties based on its actions. The environment used is cartpole v1, a standard simulation provided by OpenAI Gym. In this environment, the agent observes the state of the system, cart position, cart velocity, pole angle, and pole angular velocity, takes an action, move left or right, and receives a reward depending on how well it keeps the pole upright. The data here is not static like in classification or regression. Instead, it consists of states, the environment's conditions, actions, agents' choices, rewards, feedback for each action. We use a deep Q network to solve this task. DQN is a value-based reinforcement learning algorithm that combines Q-learning with deep neural networks to estimate the best actions over time. It enables the agent to handle high-dimensional input spaces effectively. To measure the agent's performance, we use reinforcement learning metrics such as cumulative reward, the total reward collected in one episode, and average reward, it tracks learning progress across episodes. The project is implemented in Google Colab, which is well suited for this type of computational task thanks to its free GPU access. The main tools used include GIM for the simulation environment, TensorFlow for building and training the neural network, and Matplotlib for plotting rewards and learning curves. All right, let's dive in. 2. Setup. The goal is to set up the required packages and import the libraries. Then initialize the cartpole environment. Let's import these packages or libraries. The GIM is the toolkit used to create and interact with the cartpole v1 environment provided by OpenAI. It provides a simulation where the agent learns through trial and error. NumPy helps with handling arrays, performing calculations like moving averages, and converting data types. The random module is used for random action selection during exploration and to shuffle mini batches from memory for training. Matplotlib is used to plot the learning curve, showing how the agent's reward changes over time. These are from PyTorch, the deep learning framework used to build and train the neural network. Torch handles tensors, multi-dimensional arrays, and provides layers like linear and ReLU, and Optim is used to optimize the model using algorithms like Atom. DEC is a double-ended queue used to store replay memory, a buffer of past experiences used to train the agent. Image.io is used to save recorded frames as MP4 or GIF videos showing the agent playing cartpole. Pillow PIL helps manipulate image frames before saving them, especially when dealing with Image.io. Others are used to embed and display videos directly inside the Google Colab notebook using HTML. B64 encode converts the video file into a format that can be displayed inline. Next, let's initialize the cartpole environment. This code sets up the cartpole environment, identifies the shape of the state and action spaces, and prepares the agent to interact with the simulation. The first line creates the cartpole v1 environment using OpenAI GIM. The render mode RGB array option tells the environment to generate image frames that can be saved later as video. The environment simulates a cart with a pole on it that the agent must learn to balance. The state size gets the size of the state space. In cartpole, the state includes 4 values: cart position, cart velocity, pole angle, and pole angular velocity. So state size will be 4. This gets the number of possible actions the agent can take. In cartpole, there are 2 actions. 0 is to move the cart left. 1 is to move the cart right. So action size will be 2. Note, if you get an error caused by a known compatibility issue between the latest version of NumPy and GIM, please downgrade NumPy to a compatible version. Then restart the Colab runtime from the top menu. Runtime and restart runtime so the new version takes effect. 3. Pre-training agent. The goal is to let the agent run using random actions and understand the behavior. Also, define functions to record the agent and display the video in the notebook. First, the record agent as video function. This defines a function that records a video of the cartpole agent in action. You can pass a trained model to record smart behavior, or leave it none to record random actions. File name is the name of the output video file. Max step sets how many steps or frames the video can include. The frames will store all the captured images. The environment is reset to the starting state. Let's move on to the main loop. If a trained model is provided, it predicts the best action for the current state. If no model is given, it picks a random action, useful for showing untrained behavior. This means the selected action is applied to the environment. The environment returns the new state, a reward, whether the game is over, and extra info. The render method captures the visual frame of the environment. If render returns a list, it takes the first frame. This checks if the frame is a valid image, RGB, or RGBA. If so, it's added to the frames list. If the agent fails, meaning the poll falls, the loop ends early. Otherwise, it updates the state and continues. The env close closes the environment to free up resources. If valid frames were captured, they're saved as a MP4 video with 30 frames per second. If no frames were recorded, like due to an error, it prints a warning. So this function runs a cartpole agent, captures its gameplay frame by frame, and saves it as a video file so you can visually observe its performance. This function can be used for a trained or a random agent. Next, display video function. This function allows you to embed and display a MP4 video inside a Google Colab cell. It takes one input, video path, the file name of the video. The open method opens the video file in binary read mode and reads the entire file into memory. The content is stored in the variable MP4 as binary data. This converts the binary video data into a base 64 encoded string using the B64 encode method. This allows the video to be embedded directly into the notebook without needing a separate file. It builds a data URL which browsers can play directly, then returns an HTML video player using the video tag, sets the width to 400 pixels, and adds playback controls like play, pause, volume. The SRC is the encoded video data, so it plays inline in the notebook. So this function loads a video file, converts it to a format that can be displayed directly in the notebook using HTML, and returns a playable video player. Now you are ready to run the cartpole agent. Let's run the cartpole simulation using a random agent since we don't have a model yet. Now you see the simulated video, but the poll falls quickly and restarts again, because the agent doesn't know how to take the balance. Let's train the agent in the next steps and see how it improves. Four, build DQN agent. Let's create a DQN neural network class. This class defines the neural network architecture used in the DeepQ network for the cartpole task. It inherits from NN module, which is the base class for all neural networks in PyTorch. The init part is the constructor. It receives state size, the number of features in the input, it's 4. Action size, the number of possible actions, it's 2. The super method initializes the base class NN module, which is required when building custom models in PyTorch. FC is a fully connected layer. The network architecture is 3 layers. The first fully connected layer takes the state input and maps it to 24 hidden units. This is a simple task where the input state has only 4 features and there are 2 actions, so a small network works well, such as 1 or 2 hidden layers and 16 to 64 units per layer. Of course, you can test different values. Common sizes are 16, 32, 64, and 128. Use powers of 2. Also remember that avoid going too big. If the number is too large, it can lead to overfitting unlimited data, slower training, and unnecessary complexity. The second layer keeps the size at 24 hidden units. The final layer maps the hidden units to the number of Q values, 1 for each possible action. The forward function defines how the input flows through the network when making predictions. The input goes through the first layer and the second layer with ReLU activation. Final layer outputs raw Q values, no activation. These Q values represent how good each action is in the current state. So this class builds a simple 3-layer neural network that takes in a state, processes it through 2 hidden layers, and outputs a Q value for each possible action. It's the core model used to train the cartpole agent in DQN. Next, to get action. This function decides which action the agent should take based on the current state, the trained model, and a value called epsilon. Epsilon controls the exploration versus exploitation behavior. It takes three inputs: state, the current situation the agent is in; model, the DQN used to predict Q values; epsilon, a number between 0 and 1 that controls randomness. This line randomly generates a number between 0 and 1. If it's less than or equal to epsilon, the agent chooses a random action. This encourages exploration of the environment, trying new things. If the condition is true, a random action, like left or right, is chosen. This helps the agent explore rather than always relying on what it already knows. If the agent does not explore, it converts the state to a PyTorch tensor. Unsqueezed 0 adds a batch dimension so it can be passed into the model. This feeds the state into the neural network to get Q values for each action. Then return torch argmax to choose the action with the highest Q value. This is called exploitation, using the model's knowledge to make the best decision. So it includes two behaviors. Explore picks a random action. Exploit chooses the best action from the model. This balance of explore and exploit helps the agent learn faster while avoiding getting stuck on bad strategies early on. Five, training. The goal is to train a DQN agent to maximize total reward by interacting with the environment, storing past experiences, and updating its neural network based on those experiences. The function takes 5 parameters: episodes, number of training episodes; gamma, discount factor for future rewards; epsilon, starting value for exploration rate, random actions; epsilon min, minimum value of epsilon; epsilon decay, how fast epsilon decreases. Next, initialize model, optimizer, loss, memory, and history. First, creates an instance of the DQN neural network. It takes state size and action size. This model will be used to predict Q values for all possible actions given a state. The optim sets up the optimizer, which updates the model's weights during training. ADAM is a popular optimization algorithm. It adjusts learning rates adaptively. Model parameters gives it access to all the learnable weights in the DQN model. The learning rate controls how big each update step is. So the optimizer's job is to minimize the loss by adjusting weights to improve predictions. The third line defines the loss function, in this case mean squared error. MSE measures the difference between the predicted Q value and the target Q value. The smaller the loss, the better the model is at predicting the correct value for each action. So the model predicts Q values like a brain of the agent. The optimizer adjusts model weights to reduce prediction error. The criterion measures how far off the predictions are from the target values. Next, let's set up replay memory. This creates a memory buffer to store the agent's past experiences during training. DEX stands for double-ended queue, imported from Python's collections module. It behaves like a list but is optimized for adding or removing items from both ends. MaxLen sets the maximum number of items the DEC can hold. So in this case, the memory will store up to 2,000 experiences. Each experience is a topple, including state, action, reward, next state, and done. Next, training loop. It runs the training process for a fixed number of episodes. Resets the environment to a starting state. Also resets the total reward for the current episode. Next, let's create an inner step loop. This is an interaction with the environment. For each time step, the agent selects an action using the current policy, which is getAction function we created in the previous step. It performs the action and observes next state, reward, and done whether the episode ended. The memory append stores the experience into replay memory, then updates the current state and adds the reward to the running total. If done, ends the episode early if the agent fails. The next part is learning from experience. If there are at least 32 experiences, it samples a mini batch for training. This helps reduce correlations and stabilizes learning. This calculates the target Q value. If the episode is done, target is just the reward. Otherwise, it adds the discounted future Q value according to the Bellman equation. This gets predicted Q values from the model, creates a target vector where only the Q value for the taken action is updated. This calculates the loss between predicted and target Q values, performs backpropagation to update the model. Next, epsilon decay and logging. It gradually reduces epsilon to shift from exploration to exploitation, saves the episode's total reward, prints progress for each episode. Finally, returns the trained model and reward history for plotting and evaluation. All right, now it's ready to train. Let's call this training function and store the results. The created function runs the full training loop for the DQN agent. By default, it will train for 500 episodes. During training, the agent interacts with the cartpole environment, collects experience, updates its Q values, and learns to balance the pole better over time. And the function returns two things, the model and the rewards history. The first returned value, model, is assigned to trained model. The second value, rewards history, is assigned to rewards. Once you start the training, you can see this record. In the early episodes, the agent starts with epsilon close to 1, meaning it's choosing random actions most of the time, which means exploring. It only gets low rewards, 12 to 26, because it hasn't learned anything yet and makes many poor decisions. The environment ends quickly when the pole falls, so the reward is low. In the final episodes, now epsilon has decreased to 0.08, so the agent is mostly exploiting what it has learned, taking smart actions. The rewards are much higher, about 170 to 240, because the agent has learned how to balance the pole for much longer. This shows clear improvement, meaning the agent is learning effectively. So this output shows that the agent started off poorly with random behavior, but over time, as epsilon decreased and training progressed, it learned to balance the pole effectively and achieved much higher rewards. 6. Visualization. Now let your trained agent play the cartpole game, record the episode, and save it as a video to compare with the pre-trained one. We can use the same recording function created earlier. Now we can compare the performance. As you can see, there is a huge improvement. The left one is random agent, means pre-trained model. The right one is DQN agent, means post-trained model. Before the training, the agent took random actions and the pole fell quickly, so no understanding of balance mechanics. After the training, agent learned to take strategic actions and the pole stayed balanced for long durations. Next, let's visualize the process of rewards obtained through training. Let's plot the learning progress of your cartpole agent by showing how total rewards change over time. First, let's create a function to draw a moving average, because the actual rewards are very fluctuating and a bit hard to see the result. A moving average smooths out short-term fluctuations and highlights the trend over time. It uses convolution to calculate the average of every window-sized number of values. For example, with the window of 10, it averages episode 1 to 10, then 2 to 11, and so on. Mode valid ensures only full windows are included, so the output is shorter than the input. In the next code, create a new figure with a specific size. Then plot the original reward values from the training. Alpha 0.3 inches makes the line semi-transparent for better visual comparison. Next, plot smooth rewards. It calculates a smoothed version of the rewards using a moving average window of 10 and plots the smoothed curve to show the overall trend more clearly. Line width 2 inches makes the line thicker and easier to see. Finally, add some customizations. Adds x-axis and y-axis labels. Sets a title. Shows a legend to differentiate raw versus smoothed rewards. Adds a grid for better readability. And display it. If we look at the graph, it displays the agent's total reward per episode over 500 training episodes. The blue line shows the actual reward the agent received in each episode. It's noisy and fluctuates. The orange line shows a moving average of the rewards, making it easier to see the learning trend. In the early episodes, 0 to 100, rewards are low and stable. The agent is still exploring and learning. Between episodes 100 to 250, there's gradual improvement with some fluctuation. From around episode 300 onward, there's a clear upward trend in smooth rewards. Rewards peak near the max 500 in some episodes, indicating that the agent has learned to balance the pole for nearly the full episode duration. The smooth line increases consistently, showing that the agent is successfully learning over time. Seven, save and load the data. This is useful if you want to keep your trained model. Reload it later without retraining and use it in other projects or deployments. First, save. This saves the trained model's weights to a file. Trained model state dict extracts the internal weights and biases of the neural network, not the full model class, just its learned values. Cartpole DQN-PTH is the name of the file where these weights will be stored. The file extension PTH is commonly used for PyTorch model files. Next, reloading the saved model in PyTorch. The first line creates a new instance of the DQN model. You must define the same architecture, same number of input and output units and layers as the one used during training. At this point, the model is empty. It has the structure but not the trained weights. Then load the saved weights from the file cartpole DQN into the new model. Torch load reads the file. Load state dict copies the saved parameters, weights, and biases into the model. An eval sets the model to evaluation mode. It tells PyTorch that you're using the model for inference, not training. It disables certain behaviors like dropout or batch normalization if they were used. So by using these methods, we can recreate the DQN model, load the previously saved weights, and set the model to evaluation mode. So it can be used immediately for predictions by running this code again. Okay, that's it for this reinforcement task. In this project, we tackled the cartpole reinforcement learning task, where the goal was to train an agent to balance a pole on a moving cart by choosing to move left or right. We implemented a deep queue network that interacted with the environment, collected experiences, and learned from them through training. At the beginning, the agent performed poorly with random actions, but as training progressed, it gradually improved and learned a strategy to keep the pole balanced for much longer durations. Through the reward curves and recorded videos, we clearly observed the agent's learning progress and confirmed that reinforcement learning enabled it to optimize its behavior effectively. And that's it for today's video on machine learning. We covered the foundational concepts, tools, learning types, and real-world tasks using different types of data. Let's quickly review all the learnings. 1. Introduction. The project began by exploring what machine learning is, a method that allows machines to learn from data and make predictions or decisions without being explicitly programmed. We reviewed the basic machine learning process, including collecting data, preparing it, training models, evaluating results, and making predictions. Next, we clarified the differences between AI, machine learning, and deep learning, explaining how they relate to one another in scope and depth. We also categorized the types of machine learning into supervised, unsupervised, and reinforcement learning, and identified the typical tasks associated with each, such as regression, classification, clustering, and agent-based learning. 2. Python for machine learning. We introduced essential Python libraries widely used in machine learning: NumPy and Pandas for data manipulation, scikit-learn for implementing classic machine learning algorithms, matplotlib and seaborn for visualizing trends and distributions, TensorFlow and PyTorch for building and training deep learning models. 3. Supervised learning. We studied supervised learning, where models learn from labeled data to make predictions. First, regression. We explored how to predict continuous values and evaluated model performance using metrics such as MSE, RMSE, and R2. The task was medical cost prediction. We predicted insurance costs based on features like age, BMI, and smoking status using regression techniques. Next, classification. We practiced predicting categorical outcomes with models like logistic regression and convolutional neural networks. Tasks included Titanic classification with tabular data. We predicted passenger survival based on features like age, sex, and ticket class. The second one is handwritten digit classification with image data. We use CNN to classify handwritten digits from image data. The third one is Twitter sentiment analysis with text data. We applied NLP techniques to classify tweets as positive, negative, or neutral. We also learned computer vision, explored how machines process images and videos. The task was vehicle detection. We trained a custom YOLO V8 model to detect and classify vehicles, cars and trucks, in drone footage. 4. Unsupervised learning, especially clustering. We then explored unsupervised learning, where the model identifies hidden patterns without labeled data. We used clustering techniques like k-means and evaluated them with metrics such as the elbow method. The task was mall customer segmentation. We grouped customers based on features like income and spending score to identify different marketing personas. 5. Reinforcement learning. Finally, we explored reinforcement learning, where an agent learns by interacting with an environment and receiving feedback in the form of rewards. We implemented deep Q networks to train an agent in a simulated environment. The task was cartpole reinforcement learning. We trained an agent to balance a pole on a moving cart using OpenAI Gym and monitored learning progress through reward metrics. Throughout this project, we not only covered the theoretical foundations of machine learning, but also applied them to real-world problems using structured data, images, text, and simulated environments, and gained practical experience in building, training, evaluating, and improving machine learning models. Okay, thanks for watching today's video on Coding Fab. I hope you found these tips useful and feel more confident. Remember, practice makes perfect, so try using these tips in your project. If you enjoyed this video, don't forget to give it a thumbs up, share it with your friends, and subscribe for more Fab coding lessons. Until next time, keep practicing and stay Fab.